Hi guys, welcome. So today we will be writing our very own load balancer in Java. Uh, we'll be implementing everything from scratch, from the socket level in Java, and we'll be implementing concepts like thread pool, consistent hashing, weighted round robin, and then in the end, to test our load balancer, we'll be writing a load testing script in Python. So let's get started. Let's deep dive into what is a load balancer. Okay. So load balancer is a middleware between a client and the servers. Okay. Uh, so what is the need of a load balancer? It basically, as the name suggests, it balances the incoming load of requests among the instances of the server that are available to it. Okay. So what basically servers are bifurcated horizontally. That is there might be 10 servers with 4 GB of RAM each, okay, instead of one server with 50 GB of RAM, okay. The pro in this is that if one server goes down, the other servers keep on working, okay. The single point of failure is prevented over here, which is very crucial in running a business. Okay, so load balancer also keeps this in mind that what all servers are currently working are in a good state, and then it processes the load as to which process the request as to which server should get it. Okay, so yeah, here you can see that client one wants to get access to the server, so it sends a request to load balancer. Load balancer sees which server is the most available right now, and then forwards it to that server. So here we have sent the request to server three. Server three responds back, and it's forwarded back to the client. As simple as that. It's a simple middleware. Okay. While if client 3 is making a request to load balancer, there would be a different host or other attributes which load balancer will keep in mind while choosing the server which will handle client three's request. Okay, so it might choose server 2. Okay, so yeah, there are various factors which help the load balancer determine which server should the client get for processing. Okay. So, okay, let's move on to what is the server? What is the server over here, and how does it work internally? Like the basic crux that I have implemented in this. Okay, yeah. So, this whole is a server. Okay, so this is the major crux. Okay, this is the entry point of the server socket. So, simply a socket. A socket is a simple switch, as you can understand, that is exposed to accept any incoming requests from other servers. Okay. Uh, so the socket over here is exposed on a particular port. Okay, and it is basically accepting any amount of requests at that point of time. Okay, it has no filter right now. So socket accepts the request. It wraps the request. It wraps the socket request into a object of a class that we have implemented, kind of a client. Okay, and that which is basically a runnable. Okay, so that it can be processed as a thread. Okay, then it is sent to the thread pool. Where is it sent in the thread pool? Into the queue. In the thread pool queue. Okay, and thread pool queue has various worker threads under it, which which it provides them linearly with tasks, which is inside the queue. Okay, so the basic crux of thread pool is that uh, it is initialized simply, and all the worker threads are immediately started, and their logic is as simple as that get a fresh copy of queue. Check if queue is empty. If queue is empty, go to sleep. Tell queue that to wake you up if it has a new task, otherwise let you sleep. And simple as that. Okay. And if the queue is not empty, simply pull the task from the queue and get working on the processing the request. Okay. So basically what happens is socket the initially the queue is empty. Socket gets a request. It is sent to the thread pool queue. Thread pool queue now has a task has a runnable task. So it calls a notify function, which basically wakes up a random thread worker. I said random because the choosing of which worker thread is only dependent upon the implementation of the queue that is gonna be used in the actual code. Okay, so we can say that it randomly wakes up. Okay, so it randomly wakes one of the worker thread. Okay, and simply as soon as the worker thread is activated, woken up, it checks the queue. It's not empty, polls the task, and starts working on it. Okay, so this whole structure is required for keeping a good concurrency. Okay, this is a very delicate piece of handling the socket requests, right? So, so this is the whole concept of thread pool. This is a very basic required part of the server. There are also many other things that are implemented in the server, but currently this is a very basic version of a server. So I've implemented only a thread pool some along with two algorithms of load balancing only for the instance of a load balancer, because load balancer is also a kind of server only with the capability to actually route the request to other servers. Okay, so let's focus now on to the algorithms that the load balancer uses. Okay, so first is dynamically weighted round robin. Okay, yeah. So dynamically weighted round robin is based upon a min heap. Okay, min heap basically it's a auto balancing tree structure. Okay, in it the element with the least frequency is always on top. Okay, so here we have six instances of the server. Okay, basically server is a class, belongs to a class of server, so which has two attributes: server name, which is the full address, full address, which includes the IP address along with the port number. Okay, and the load. Initially all the instances of the server have zero load. Okay, because they are not processing any request at the time. Okay, so this is T1, this is T2, and this is T3, another named already. So initially, this is the heap. In Java, we implement the min heap through priority queue and with a reverse comparator. Okay. So yeah. So T1. So basically, load balancer gets a request. Okay. Now it has to process a request. So it fetches a server from the priority queue with the least frequency, which is currently T1. All of them have the least frequency because all of them are zero. But fortunately for us, T1 is at the top right now. Okay. So T1, it fetches T1. Okay. Get server, it calls T1. And when the get server function is called, it increases T1's load. Okay. By one. So now T1's load has increased. So the queue, the min heap will auto balance itself. Okay. So T1's load is more than T2's now. So T2 and T1 will swap places. Now, okay, this is T2 and this is T1. Now again, T1 has more frequency than T3. So it will again swap places with T3 as well. So this will happen. Okay. And now T2 is at top. Okay. So this keeps on happening. The load keeps on increasing. The reordering keeps on happening, and always the server with the least load will always be on top. This is a good thing because obviously the heavier server, the heavy server processing the maximum requests at the time should not be bothered. Okay. The server with the least amount of requests that is being processed in it should always be on top and should be required by the load balance all the time. Okay, so yeah. Also, one more thing. The load does not keep on increasing only because server is get. There is also a function called release server. As soon as the request is processed in the load balancer, a release server function is called with the server name, and the server which has been relieved gets its load decreased by one. Okay. So yeah, now if the T1 gets relieved quite a lot easily than T2 and T3, it will go back on top. It will stay on top most probably easily, right? This is the basic logic of dynamically weighted round robin. Now let's move on to the other load balancing algorithm, which is consistent hashing. Okay. Okay. So consistent hashing basically is based upon a circular map. Okay. Each server is mapped with a particular hash code or a quantized value, as you can say. Okay. So we have six servers: T1, T2, T3, T4, T5, T6, and each of them have been given a quantized hash code value. Okay. So now, if a request comes in, the request is also hashed with the same function. For example, now the request has a value of 150. So it's lies somewhere here, around here, right? 150. So which server will be responsible in handling R1 would be T2 because that's the next greatest server in comparison to the hash code that it got, the map got. Okay. So, for example, let's assume that T2 should be processing this R1, but unfortunately for us, T2 had a failure and is not working right now. Okay, so it's not processing right now. So the load will automatically go to the next greater hash code actually. Okay, so it will go to T3. Okay, and this is exactly how it keeps on happening. Okay, if a server if a request comes in with a value of 601 or above, so as you can see, there is no server with a with a value greater than 600. Okay, so what we do is we reroute the reroute the request to the server of the or to the initial server in the map, okay, which is T1 here. But if the T1 would not be working, T2 the T2 might be the initial value initial element in the whole map, right? So it will be routed to the initial element in the whole map. Okay, this is why it's circular. So, okay. So this is the basic implementation of what I have done in consistent hashing here in the load balancer. But there is one more thing that you guys can implement on your own. Okay. So this is not fully efficient because this does not guarantee a very good load balancing still. Okay. What is missing is that, for example, if T, for example, T1 T1 goes down, okay, T2 goes down, right? And yeah, T3. So any request that comes like with 600 plus or 100 or 100 above or 100 less than 100 will all be processed by T3 and T3 only. T4, T5 and T6 will be chilling. They would not be having any work to do. Okay. So that is just wrong. This is not a good load balancing. So what we do is we put virtual nodes pointing towards the original servers throughout the map. Okay. They are not actual servers. They are just pointers towards the actual map. We still have the only 6 servers. So what would happen is this is T2 alpha. This is T5 alpha. And this is T4 alpha. The placing order right now is not exactly very based upon any algorithm right now. It's I have randomly placed them, but obviously the ordering is still in a particular based upon some algorithm. So yeah, so basically what happens now is, for example, T1, T2 are out. Okay, so any request that comes with a greater than T6, it goes to T2 alpha. But of course T2 alpha is not working. So this is T5 beta. Okay. So any request that comes after T6, okay. So it will go to T5 beta. T5 beta points directly to T5. Okay. So any request in here in this range will be processed by T5. Any request in this range will be processed by T3, and so on. And any request within this range will be processed by T4. Okay. So these are just pointers to getting which server will be responsible right now. So increasing the virtual nodes just guarantees an equal amount of balance of load or slash requests among the servers that there is. It is like increasing the surface area uh, for getting a hit of requests. Okay. Now, if we have 5 virtual nodes of T4 as well, so the surface area of getting of T4 getting picked for a particular request is more now. Okay, so and that happens for every server. So the surface area for every server should be large, so that so that there should be many redundant layers, so that not one single server should be responsible in the end for handling a big amount of requests. Okay, yeah. So this is the whole theoretical portions. Now we'll be diving deep into the code. I'll be explaining you guys the my written code line by line. Okay. So yeah. Yeah, so guys, here is the code. Okay, we are gonna start with thread pool. Okay, thread pool class. So we have an array of worker threads. Okay, so the size of the array depends upon the thread pool size. Okay, and here we have a simple queue which accepts a runnable into it. Okay, so
in this constructor, we're initializing every data member. Okay. So as soon as the workers are initialized, okay, they are started as well. They are started immediately. Okay. I'll explain you guys why they are started immediately. So this add and execute function is the entry point for the thread pool. Okay. So our enable is sent in the arguments. Okay. The This function gets a synchronized fresh copy of the queue and adds the task into that. Okay. Once the task has been added, the queue calls a notify function. What notify function does is any thread that is using the queue.wait, okay, is basically sleeping. The thread is sleeping, which is using queue.wait. What queue.notify does is it wakes up one of the threads randomly and it tells you that you don't have to wait now. You can start the process now. Okay. So this is the worker thread class. Okay. It extends the thread. So when they're started, the run method is called immediately. So here we are again using the synchronized keyword for the queue. Okay. So it checks if the queue is empty. If the queue is empty, the thread has to wait. There is no task for the worker thread to do, right? So it calls queue.wait. Okay. It is in try catch because there is a chance that the thread can be interrupted by some external process. So therefore, so queue.wait. Okay. So whenever the queue.notify is called called, right? Uh, any thread that is waiting will be reactivated. So this whole function again gets called. Okay. So it will get a synchronized copy of the queue. The while loop will be executed. It will check the why if the queue is empty or not. Queue is not empty now because something has been added, and after then only the queue is notifying one of the threads. So the queue is not empty. It will break out of the loop. It will assign the runnable into the task variable over here, and then the task will be run by the worker thread. Okay, simple as that. So this basically keeps the things very concurrent and very linear. Okay, so that there is no race condition from the threads of getting a task basically. Okay, so yeah, this is the thread pool. Okay, but one more thing. Instead of implementing all of this dot notify, dot wait, etc., there is a class in Java which does this all inherently, okay, which is a linked blocking queue. Okay, I've commented it out because basically this does not. If I would have used this, would not be able to teach you guys how the thread pool basically works or how the queue.notify or the queue.wait works, because this class also utilizes this concurrent locks only for the for keeping keeping the concurrency in check. Okay, so the two major functions that this class has, which replaces the add, notify, and wait are, uh, it is the q.put. Okay, what the q.put does is, right? Q.put does is it works as a add and a notifier. Okay, it adds the task and then automatically notifies the threads. Okay. Over here, we do not have to write this code of while queue is empty, go to sleep, queue.wait, right? It will simply, we have to just call queue.take. This function will block the whole thread until unless there is a task in the queue for the task. Okay. So here simply we take the task and then we execute it. We do not have to keep a while loop running and then we have to poll it. Okay. So this is a very professional or production ready logic that we should use in a production grade software. Okay. Uh, and like this is using a simple queue is just for explaining you guys how this whole concurrency handling works in thread pooling. Okay. So now moving on to the load balancer. Okay, we are going to implement the load balancing algorithms. So yeah, here I have implemented an interface of load balancer, which basically which the servers require. Okay, or servers or any of the external classes require from a load balancer. The load balancer should be able to add a server, remove a server, get the server based on the request. Okay, it calculates which server it should pick. This function is the function which picks the server based on a logic. Okay. And then to relieve a server, if the request has been processed, we can relieve the server now that it's been done, so that load balancer knows that this server is not processing this request anymore, so it can lower its load now. When the server is get, it increases the load. Okay. The load logic is not a part of consistent hasher. Okay. So we do not use any, we do not have to worry about any load logic over here. The load logic is for dynamic weighted round robin over here. Okay. So yeah, so here I have implemented the four functions along with one get hash function, which is a utility function over here. Okay. The best thing about this implementing the interface is we are using the strategy Java code pattern. Okay. So in my server class, all I'm doing is accepting a load balancer type. What is a load balancer type? It's a simple interface actually. But when I'm actually implementing this whole server class, server object, what I'm doing is sending a class that implements the load balancer. I'll show you guys. Go ahead. So I created this dynamic weighted round robin object, okay? And then when I'm creating a new server, I'm sending the dynamic weighted round robin object over here, which is itself a load balancer. This logic is a load balancer. While here I've commented it out, but if I'm using consistent hasher, is it also requires, it does not require any new adjustment to the constructor. It also accepts the constructor also accepts the consistent hasher, because consistent hasher is also a load balancer. Okay. So this is the pro of using strategy coding design pattern here in Java. So moving on to consistent hasher, the logic here is adding the server. Okay. So we have a hashing function which basically gets a quantized value of the server address. Server address basically consists of the IP address and the port number of the server that we're going to send it to. Okay. So basically what it does is it hashes the whole server address and gets the hash, and it's put into the sorted map. Okay. Why it's called a circle, I'll explain you guys in the get server method actually. So basically, I have used a sorted map over here. Okay. Sorted map is used because remember when I was explaining you guys consistent hashing, whenever a request comes in, the request is quantized into also quantized into onto hash value. Okay. So to get a server, we simply need to find a server in the whole consistent hashing circle, which is just greater than the quantized value of the request. So for example, the quantized value of the request is 150, and the next server in the whole circle is 200, so, which pertains to the server 2. So server 2 will be picked here. Okay. Let's assume that for some unfortunate reason, server 2 is down. Okay. So the next greater hash value is belongs to server 3, which is 300. So server 3 will be picked. So this is how that server function works. Okay. Yeah. And then here is the remove server. Works simply the same way. And then we have the get server function. Okay. It first checks if the map is empty or not. If the map is empty, we don't have any servers. Okay. So, okay. Now what it does is the get server function actually gets the request as a string. So it hashes the request. Okay. And it gets the quantized value, right? The big integer. Okay. Now it will check if the circle does not exactly have that hash value. Okay. The hash value does not exactly match one of the server addresses. What it will do is try to get the nearest greater match to the hash value. Okay, so this function basically gets a submap of all the items whose key is equal or greater than hash value. Okay, so now it will check if the tail map is empty. That is, there is no server that has a hash value greater than that in the request hash value of request. Okay, so it will simply, just to make it a circle, it will simply circles first key, which is server 1. So yeah, if the quantized value of the request is 601 and the last server's hash value is 600, so there is no server which has a value greater than 600. So it will be returned back to the first server, which is server 1, which in here in this case is dot first key. Okay. Otherwise, the next greatest server with the hash value will be picked from the tail map, from the submap that is created over here. Okay. And then the hash will be saved in this in the same variable. And then uh, the server that belongs to the particular hash is returned. Okay, so this is how the get server function works. Oh, sorry. I guess I went wrong. Okay. So there, here is the get hash function, basically. Here in consistent hasher, we do not have a very necessary reason or a need for a release server function. So I just put a system logging logic over here. Okay. So here is the hash function. Okay. So it simply uses MD5, okay, to hash a string and return it as a big integer. Okay. Now here, why have I used salt? Well, it's because if I want to test my request, okay. So every time my request will hit the server, it will always be the same in a string because I am hitting it from my local host. So it will always be the same. So just to test it, just to spice up the key, the string, I've added the salt. I've prepended the salt actually. So yeah, so this is the reason I've used sort over here. Okay, no security purposes or whatsoever here, just for testing. Okay, and then now we can move to dynamic weighted round robin. Okay, so in this we have a subclass basically, right? So anytime a server is add server is called, okay, the server address is a new object of the server is created. Okay, it's a subclass. It has two values: the string, which is basically the address, and the load. Okay, so and also the load is of type atomic integer. Atomic integer basically has a special feature in it, which basically makes any transaction done on that particular integer atomic, which means that uh, the set of operations done on that particular variable uh, are treated as one only. So as to prevent any race condition or non-concurrent behavior from multiple threads. Okay, so that this particular variable will not be corrupted. Okay, in short, so we have these three functions: increase, decrease, and get load. Okay, and over here, okay. So in the add server, and to be honest, in all of the functions, I have used the write log functionality. Why have I not used the synchronized bit? Well, just to teach you guys some better methodologies of handling concurrency. Okay, I could have simply used the synchronized keyword over here, and it would work the same over here because in all of the function I'm doing writes in the attributes of this class. Okay, but just to show you guys different and better methods of handling concurrency, I've used the write log over here. There are two types of logs. Okay, one is a write log and one is a read log. If any thread has a read log, no other thread can read the particular snippet of sorry, the attribute, the data members that are inside that scope. Okay, while while if a thread has a write log, none of the threads can either read or write to that particular data member. Okay, so yeah, I retrieve the log over here, and then I add the server. I create a new server object. I add the server to the queue and create a key value binding with the server address to the server object. Okay, and then in the finally block, I unlock the log. I relieve them. This is a very required part of handling the concurrency using logs, because if you do not unlock, you are basically causing scarcity among other threads for using this add server function. Okay, no other threads would be able to access this add server function. Okay, so okay, now again we have the logic of remove server, which is also very simple. Just speciality is that we are using the write log and we are unlocking it. So here is the here is the get server function. So it checks if the server queue is empty. It's not. Okay. If it's empty, we obviously don't have any service in our system. Okay. So now what happens is in the server queue, we poll from the server queue because the server with the least amount of load will always be on top. Okay. So it will poll it. So this guarantees of always getting the server with the minimum amount of load, the server which is handling the minimum amount of load. Okay. So what we'll do is increase the load. This function, by the way, does an atomic operation, okay? Because it increases the load attribute of the server, which is an atomic integer, okay? This itself is handling concurrency pretty good. And now, in the end, we add the server back to the server queue so as to restructure the whole queue, okay? So yeah, and then we return the server.address for a server to forward the whole request. And then finally, we relieve the lock. In the relieve server, now here we have an implementation of the relieve server function actually, because here we have to relieve and decrease the load on the server when the server actually processes the request. This function is called when the request has been processed. Okay, so we get the server from the map, and then we decrease the load, and then we add back to the queue to restructure it, and then we finally unlock the lock. Okay, so this is it for dynamic weighted round robin. So next we'll be moving on to the server, okay, which is the complicated part.
All thing that I missed, guys, that I put a try and finally in here, right? But I was returning the server address and then calling the unlock after that, which would have which was like logically incorrect. So I removed the try and catch because we do not require them at this point right now over here.
Okay, yeah. So here is the server class. Okay. So basically, the server has two constructors. Okay. Because as I said before, the server can be treated as a load balancer or as a standalone server. Okay, which the load balancer will forward the request to. Okay. So here are the two constructors. If the load balancer is sent from the implementation, this will be now a load balancer. Otherwise, load balancer data member will be null, and therefore treating it as a standalone server. Okay. So as this implements a runnable, obviously all the servers will be run as a thread so that they don't block the main thread. Here's a run function. I've implemented these two util functions called log and log error just to simplify the system.out.println bit. Okay. So here we have the server socket. Okay, we put the server socket in the try scope. Okay, and we open our server socket on the particular port that we have is initialized in this constructor. Okay, the server is listening now. Okay. This is to keep the interruption in check. Okay. Otherwise, if any interruption occurs, the whole server will shut down. As simple as that. So this is the bit which keeps on looking out for any requests of sockets that come in. This is the bit that keeps on checking on the exposed bit of the socket that if a connection request is made, it will accept the request and then depending upon the type of server, it will send to the handler. It will send to the thread pool. Okay. So, yeah, we have estimating that we have now a client socket. Okay, I will wrap it into a new client handler object. Okay, uh, yeah. So, and then I will add it to the thread pool. I'll not process it right away. I'll send it to the thread pool. Thread pool will execute it on its own. Okay, this uh, this is why we implemented the thread pool. So add and execute. Okay. And the client handler is itself a runnable. So therefore, as we know that add and execute uh, accepts a runnable to add it into the queue. Okay. So whenever the worker thread finally runs this task, client handler. Okay. What happens is, as you can see, the client handler is also divided into if it's the client handler of a load balancer or not. Okay. Okay, so what will happen once it's run is if it's a load balancer, it will call this function. Otherwise, a simple request to the server bit is called. Okay, so here we go. Yeah, so gonna go into this. Okay, so what do we have here is the we will open the input stream from the client socket, and then we will create a new input stream reader and put into the buffer reader. Okay, which we will call the client reader. Okay, so then we will send the request. Basically, this is basically the load balancer processing a client's request. Okay, so he has to forward this request to the server. Okay, so what this bit does is it will read the request. It will read the first line from the request. Okay, to create a hash value. Okay, to create a hash value, and then sorry, not to create a hash value actually. This request line is the initial vector which the load balancer will use to getting a server. It is used in consistent hashing or the dynamic weighted round robin. So yeah, uh, yeah. So load balance. So we can see the load balancer that has been implemented over here will get the server. Okay, whether it be dynamic weighted round robin or consistent hashing, doesn't matter. We have implemented this function. So it will get the server. Okay, it's a string with a host and the port. Okay, and then we will send to the function called forward request. As simple as that. It will process the request. It's a bit complicated over here. We will first get the server address. We will check if it's a server address is valid or not. This is not a very good validator though. It simply checks that the address should contain the host or and the port, right? Though there are other applications that we have to also keep in mind when creating a validator. Okay, so over here we get the target port. Okay, then now we open another socket from the load balancer to that server. We open a socket. Okay. So now what we're gonna do is after we have opened the socket, we're gonna get the output stream, okay, into the print writer. We will gonna create all the streams from app loader to server and a reader for a request that comes from the server back to the app loader. We're gonna create a reader, okay, the server reader, and then after reading that request, we also have to respond to the client, right, from the load balancer. So we are also gonna create a output reader, basically a print writer from load balancer to the client. So this is that, okay. To make it more understanding, this is what server writer. Yeah, this is load balancer to server. This is server back to load balancer. Okay, uh, and this is load balancer to client. Okay, so these are util functions. Okay, I'm gonna show you guys. They also just simply use various buffer readers and print writers to forward and get the request. Okay, so yeah, as it is simplified, have the server writer. We send the whole initial request that we read from the client to the server. Uh, so you guys can change, of course, the what you want to send and how do you want to interpret it on the server. It's just how I have implemented for the POC over here. Read and forward headers. This will that was just sending the initial request, and now we're going to send the whole headers. Okay, so it will read and forward the headers. Okay, it will read the line, immediately send that line until we have reached a null pointer. Okay, and then we will send a ending request to the server that the load balancer to the server request is now finished, so that server can stop reading now. Okay. Now, because now we have send the server the request, it will be processing it. So, and obviously we have got it. So now, according to the load balancer, we are going to relieve that server now. So that's why we have called the release of function. Okay. And now after that, the server will respond back to the load balancer. Okay. Which we are going to we are going to read using this function, read and forward response. Okay. So this is it, server reader and client writer. So we are reading from the server using the server reader, buffer reader, and then as soon as we are reading it, we are sending it to the client directly. Okay, as simple as that. Okay, and then finally we close the socket. Okay, as simple as that. Yeah. So this is the bit where the load balancer is handling everything. Now to see the POV from server. uh, uh, an instance which does not have the load balancer attribute. Okay. Ha- So now if the load balancer data member is null, so basically it means the server is a standalone server, so it will handle direct client request. Okay. So what it's gonna do, simple as that, it will get an input stream from the client socket, open a print writer for client writing because it will read it simply. We have a client reader, and then we are gonna send it using the client writer, right? So here we have it. Okay, as you guys can see, this is pretty simple now. Okay, we are not using, as I said before, we are not using any data from the request. We are just reading and receiving it. You guys can use this request if you want. And now we are gonna create a response from the server to the load balancer, which will be served back to the client. Okay, which is this. Okay, hello from server on port number. This is this to so that I can know that this response is from this server, so that I can know that load balancer is rerouting it to other servers as well. It's not just it's working actually. Okay, and now the server send response, simple as that. Okay, and now finally close socket. Okay, so as simple as that. All right. So this is the basic server handling, and I'll be writing a script in Python for load testing. Okay. In the next part. Okay. We're gonna test our code. So I have written a script in Python. Okay. This basically starts a thread pool of 30 threads, or with a basically with a maximum of 30 threads, as you can say. Okay. It accepts the number of requests that you want to make and the port on which app load balancer is run. Okay. And it counts the total number of success and the failure. Okay, as you can see. And it also prints the response from the servers so that we can see that response was from which server. Yeah, right. So, yeah. So now I'm gonna show you guys the implementation of our classes in the main class of the Java. Here you can see I have implemented an array of 10 servers. Okay, this is the port range. All the servers will range from 1004 to 1014. Okay, and I'm using dynamic weighted round robin algorithm over here, and I'm initializing and starting the servers over here, along with adding them to the weighted round robin load balancer. Now here I'm initializing the load balancer and starting it as well. Simple as that. Okay, so let's get started. Okay, so all of our servers are running now, as you can see, with every port. Okay. Okay, load balancer is also running now. Cool. So now what we're going to do is we're going to bombard them with requests from our load tester. As you can see, I have tested it with 1000 requests right now. Okay, let's test them again with 1000. Okay, so it looks like all of our requests were success. Uh, as you can see, uh, yeah. So basically, the distribution is pretty equal among all the servers. As you can see, the diversity over here, the responses, right? It's pretty good. And there is no failure. So basically that means that all of the sockets connected and all of the sockets were returned. Okay. So let's do one more thing. Let's increase the number of threads. Okay. The maximum number of threads at once. And let's test it again. Okay. So 50 coherent, sorry, 50 concurrent threads, and yet still fully 100% success. Okay. So basically our load balancer implementation is fully working correctly. Uh, so yeah, I'll provide the code in the description, guys. Okay, you guys can if you guys want to read the whole code or copy it and want to modify it, you guys can. Okay, I'll provide the GitHub link down below. So thank you guys for watching, and see you guys in the next video.